Welcome to a new chapter in our Calculus 2 course. This one is entitled Differential Equations. Little intro. The laws governing our physical universe are widely written in the language of mathematics. When static problems arise, algebra can solve many of them, but other natural phenomena involving change are best described using equations that involve variables that in turn represent changing quantities. The most natural way to describe changing quantities is using derivatives, since expressions like dy dt describe how the variable y changes with respect to time t. So we define a differential equation as an equation that involves derivatives. Pretty simple. As an example of such an equation, we can consider y double prime minus y single prime minus 2y is equal to 0. It's actually easy to verify that y is equal to e to the 2x is in fact a solution for this differential equation. Indeed, if y is equal to e to the 2x, then what's y prime? Well, it's e to the 2x times the derivative of the exponent 2x, so 2e to the 2x. To find y double prime, we derive y prime, we find 4e to the 2x. Hence, what we get here is, well, y double prime minus y prime minus 2y will end up being 4e to the 2x minus 2e to the 2x minus 2 times y itself, e to the 2x. That's 4e to the 2x minus 4e to the 2x, and that is 0, and it verifies that the equation is satisfied when y is actually equal to e to the 2x. One of the purposes of this section is actually to find solutions to differential equations that we can abbreviate DE. We will focus our attention on one particular type of differential equation known as separable variables. As the name suggests, a separable differential equations has the property that both variables involved in the equation can be isolated separately from one another on either side of the equal sign. For example, the differential equations dy dx equals to 2 root y over 1 plus x squared is a separable equation. Indeed, multiplying both sides by dx, what do we get? Well, dy is equal to 2 root y over 1 plus x squared dx. Now, if we divide both sides by, root y, we will obtain dy over root y is equal to 2 over 1 plus x squared dx. Now we can actually see here that all the y's are isolated on the left side of the equality, while all the x's are on the right side. So in order for us to actually solve that equation, it would make quite complete sense to integrate both sides in order to find what y equals f of x. So what do we get if we do just that? Well, we're going to get the integral of dy over root y is equal to the integral of 2 over 1 plus x squared dx. Root y is y to the 1/2, bring it up, y to the minus 1/2. So that's 2 root y, and the integral of 1 over 1 plus x squared is arctan. So cancel the 2's on either side, we get root y is equal to arctan x plus c. Please notice that it is sufficient to put the plus c on one side only. Having c1 on the left and c2 on the right simply amounts to having c2 minus c1 on one of the sides only. So calling c2 minus c1 c, we have the solution to our differential equations, which is really root of y all squared is equal to arctan x plus c all squared, or simply y is equal to arctan of x plus c all squared. So to summarize what we have done, we can actually say that the step of solving a differential equation involves 4 steps. If the equation has a y prime, change the y prime to dy dx, that's my step 1. Now in step 2, isolate all the y's on one side and all the x's on the other side. That's an algebraic step. In step 3, we integrate both sides, so that's more of a calculus step. And finally, whenever possible, it's not always possible, we actually find what y is in step 4. Well, let's see a couple of examples on how this pans out. Here we have dy dx is equal to xe to the minus y. So step 1, no need because we already have dy dx and not y prime. Step 2, we isolate our variables. So kick the dx to the other side. Dy becomes xe to the minus y dx. Now we're going to bring e to the minus y on the other side, so we're going to divide. But of course, division by e to the minus y is multiplying by e to the y. So we get the end of step 2, e to the y dy is x dx. Integrating both sides, these are very easy integrals. We get e to the y equals x2 over 2 plus c. And it's not very difficult here to actually get the y from this last equation. We take the ln on both sides, not forgetting to take the absolute value, of course. And since the ln of e to the y is just y, we have our final solution. Y is the ln of the absolute value of x squared over 2 plus c. Here's another example. This time, y prime is the secant squared of x plus 2y prime. So step 1, we need to change the y primes into dy dx. So this y prime becomes dy dx, and so does the other. We bring all the dy dx to one side, and we get this expression, out of which we factor out dy dx. So 1 minus 2y is dy over dx, and I am left on the right side with secant squared of x. I take my dx, I move it to the other side, so that now truly I have all the y's on the left and all the x's on the right. Integrating both sides, the integral of 1 dy is y, and the integral of 2y is 2y squared over 3. While on the other side, the integral of secant squared x is tan x plus c. Now here, as you can probably see, it's going to be pretty difficult to isolate the y from that. So we're going to leave the equation in step 3 as our final solution to this equation. Sometimes in differential equations, they actually come with something called an initial condition. That's actually a point xy that belongs to the solution of the equation. Being given that initial condition enables us to find the numerical value of the constant c. Let me show you how this works. So example 3. This one starts with this du dt is 1 minus t squared over ut squared plus u4 t squared. And here's your initial condition. U at 1 is equal to 0. That simply means that when t is 1, u is 0. Okay, so we already have Leibniz notation here, du dt, no need to do any step 1. Step 2, what are we going to do? We are going to basically isolate our variables by, first of all, taking a t squared out of the bottom expression on the right-hand side, hence getting t squared multiplying u to the 1 plus u to the 4. Then we can cross multiply, and we basically get u plus u to the 4 du is 1 minus t squared over t squared dt. So now all the t's are on the right and all the u's are on the left. We are ready to go to step 3 and integrate. So we integrate, again, easy integrals. The integral of u du is u squared over 2. The integral of u to the 4 is u5 over 5. While here, it is best to break this right here in half of the fraction. So 1 over t squared is t to the minus 2. T squared over t squared is 1. Now the integral of t to the minus 2 is t to the minus 1 over minus 1, which is the same as minus 1 over t. And the integral of minus 1 dt is minus t. We put our plus c here. Since this is difficult to actually find what the u is, we're going to leave it like that. But we still have the initial condition to take care of. So what we're going to do here is we're going to replace t by 1 and u with 0 in this part. So we get 0 squared over 2 plus 0 squared over 5 is equal to minus 1 over 1 minus 1 plus c. 0 on the left, minus 2 plus c on the right. So c is 2, giving me my final solution. U squared over 2 plus u 5 over 5 is equal to minus 1 over t minus t plus 2. It's not elegant, but it is the right solution to this equation. Let's follow right away with another example. Example 4, p prime is equal to t squared p minus p plus t squared minus 1 with an initial condition that p of 3 is equal to 0. So step 1, we have, first of all, we were given Newton's notation, so we need to change that to Leibniz. So P prime becomes dP dt. On the right side, I noticed that if I factor out a p from the first two terms, I'll be able to do double factoring. So I do just that. So that's p plus 1 times t squared minus 1. Makes it easy to isolate the variables because now p plus 1 goes under the left side. So I get dp over 1 plus p is equal to t squared minus 1 dt. So we can integrate this. The integral of 1 over p plus 1 is the ln of p plus 1. And here the integral is t3 over 3 minus t plus c, raising both sides to the power of e. In order to make a little bit of an effort and find what p is, we actually take p to be e to the right-hand side and the minus 1 on the other side. And now we take care of the initial condition. So the initial condition, p of 3 is equal to 0. That means I replace my t with 3, and I replace my p with 0. I end up with e to the 6 plus c is equal to 1. Now I want c, so I'll ln both sides. ln of 1 is 0. So that means that 6 plus c is 0, so c is minus 6. I replace it back into my solution, and I get that p is e to the t3 over 3 minus t minus 6 and minus 1. Good. Enough of solving this. Let's take a look at some of the applications. So we turn our attention to one of the most important differential equations in terms of its applications in the fields of social science and science. This equation is used to model the population growth where there are no external influences. Population can be a bacteria in a petri dish, animals in an enclosed area, or human population in a country, or so many other possibilities. This differential equation that is used to describe population growth is based on the following observation. Consider a population that doubles every minute. Say we start with 1 bacteria at time 0. Then the number of bacteria at different times can be described by the following table. So at time 0, 1, doubles up after 1 unit of time, so 2. 2 doubles up to be 4 after another unit of time. Another unit of time, 4 becomes 8, and so on and so forth. What's actually more interesting than anything else is to look at the rate of change, the average change in the population per unit of time, so per minute. If you look at the table here, from 1 to 2, delta p over delta t is 1. From 2 to 4, the delta p over delta t is 2. Then it's 4. Then it's 8, then it's 16. And out of this comes the crucial information that the larger p is, the larger delta p over delta t will be. For a p of 32, delta p over delta t is 16. Bigger than, for example, if p is 8, then the delta p over delta t is 4. That is to say that p, the population, is directly proportional to the average change, delta p over delta t. The symbol we use for that is that little squiggly alpha. So p is proportional to delta p over delta t. If instead of the average change in the population, we were interested in the instantaneous change, we would have to take the limit as delta t goes to 0. Of delta p over delta t, and we would be calling this dp over dt. Hence, our proportional thing would actually become p is proportional to dp over dt as delta t goes to 0. Another way to write proportionality, you may remember, is actually to use a proportionality factor of k. So kp equals dp over dt. K is the constant of proportionality of this separable equation. Solving it actually gives something quite elegant that we have all seen before. dp over dt is kp. Bring the p under. Integrate. The integral of 1 over p dp is ln p. And the integral of k dt is kt. We put the c1 there. Bringing both sides to the power of e, I get that p is e to the kt plus c, and I break this in 2. And e to the c1, I decide to call c, and I get p is equal to c e to the kt. Now suppose that the population at time 0 is actually given by p0. replacing t is equal to 0 in the solution p is equal to c e to the kt actually yields p0 equals c e to the 0 times k. And since e to the 0 is 1, c is p0, which actually gives us the final form of the solution to this differential equation, p is equal to p0 e to the kt, where p0 is the initial population, p is the population at time t, t is the time elapsed, and the growth constant is k. As previously mentioned, this differential equation and its solution is very useful in modeling a wide array of situations. Let's take a look at a closer number of these applications in our very next lesson.